Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's get going right away. I want to make sure that we have an opportunity to do a couple more applications of L'Hopital's rule together, particularly when our original indeterminate form is not a quotient and does not authorize the use of L'Hopital's rule. Then we're going to develop our final antiderivative rules today, and as you notice a common theme in those last three questions, they're going to involve trigonometric functions. So today is all about getting our final antiderivatives for transcendental functions and our trigonometric functions while we're still working with exponentials and logarithms. So let's get cracking. We know we can differentiate an exponential with any base. We just need to take into account the natural log of the base. And so the derivative with respect to x of an exponential function is the exponential function itself times the derivative of the exponent. Tangent differentiates to secant squared, nice little memory there, times the natural log of the base. And so I don't know if there's a way to make this look much prettier, but we know our derivative is the exponential itself times the derivative of the exponent times the natural log of the base. Raise your hand if you had this already. So who had number one already? Great work, you guys. Can we differentiate a composite function? Absolutely. We've got the chain rule. The key is starting with the correct words and then keeping track of how many links are in our chain. So let's go ahead and firstly, Kyle, box that. Firstly, let's consider my overall function. So think of this overall function here. Is it a trig function? Is it a linear function? Or is it a square root function, a radical function? Well, overall here, my outermost function, in this case, matches. It is a power rule. This is a radical function. And so in my head, I'm thinking this is asking me to differentiate secant of 3t all to the 1/2 power. So in my head, I'm thinking this is asking me to differentiate secant of 3t all to the 1/2 power. So I'm going to go ahead and start out with my power words. The derivative of a power function is the exponent, the current exponent of 1/2, times the base raised to 1 less. 1 less than 1/2 would be negative 1/2. That's negative 1/2. Awesome. Times the derivative of the base. Well, my base in this case was secant of 3t. So now I'll go ahead and do the derivative of the base. And the derivative of the base is the derivative of secant 3t. So I've got 2 more links to go. All right. So what's the derivative of the trigonometric function? Well, a derivative of the trigonometric function is the derivative of the trig function with the angle, and then times the derivative of the angle. So now here we go. The derivative of secant is secant tangent with the angle, then times the derivative of the angle. So it looks like we need a secant 3t, tangent 3t. I was trying. It's not going to work. Times the derivative of my angle. So we've got our 3t's in here. And can I do one more? I think I can. I can scooch another color in here. All right. So did we get our entire chain rule? The derivative of a power function is exponent times the base raised to 1 less times the derivative of the base. There's our derivative of secant 3t, which is the derivative of the trig function with the angle, then times the derivative of the angle. Did we get everybody? Yay! Final answer. What a mess. Bless you. Let's go ahead and rewrite this so it looks a little bit prettier. I'm thinking we'll grab the 3, the secant 3t, tangent t, leave it on top, kick down the negative exponent, and rewrite it as a radical on bottom. So let's go ahead and do that. I'm thinking 3 secant 3t, tangent 3t, all over 2 radical, sound effect of course is optional, secant of 3t. Do we get everybody? Did I miss anybody? Got it. Awesome. Raise your hand if you had this. So anybody have number 2 already? Yes? Yes, 2. Good. We're closer. What happens if we're asked to go backwards? That is, evaluate an indefinite integral. Remember, evaluate an indefinite integral is the same as finding an antiderivative, an antiderivative function, right? Such that when differentiated, produces the original integrand. We know that our sum and difference rule for taking derivatives holds true when we find antiderivatives that go backwards. And so I can handle this separately. I could go ahead and find an antiderivative function for that cosecant squared x, and then I'll go and find an antiderivative for that e to the negative 4x. I'll just break up that sum or difference and handle one at a time. All right, so we need to remember our words. We just saw how tangent differentiated to secant squared, right? Secant squared, and that hopefully reminded you that cosecant squared must then integrate to cotangent, right? A cotangent of x, except for one problem. We needed the negative sign, right? The negative sign. And so this first one, we don't have to provide, right? We don't have to provide any derivatives of the input. We've got a negative built into our antiderivative. So it looks like negative cotangent of x is an antiderivative for that first squiggle blue underline. How come? Because when you differentiate cotangent of x, we get negative cosecant squared of x. Therefore, if we were to differentiate negative cotangent x, we would get the positive cosecant squared x in my original integrand. What about the e to the negative 4x? Well, that's a little bit trickier. We know that my exponential base e functions are easy to differentiate and integrate rather, because they're cyclical. The derivative of e to the x is itself, e to the x. But this isn't e to the x, it's e to the negative 4x. And so, if I were going backwards, I would say that this comes from an exponential function with the same exponent, because the derivative of an exponential function is the exponential function itself. Therefore, an antiderivative of an exponential function must be the exponential itself. So e to the negative 4x. However, my exponent wasn't plain Jane x, it was negative 4x. And so what do? Well, we need to account for the fact that the derivative of the exponent, negative 4, was not present. So what constant must we add here? Right? Sammy? Absolutely. And so I'm going to include a negative 1/4 in my antiderivative. And always, 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 if we're evaluating an indefinite integral, what must we include? A plus c, count baby, a plus c. So we better have our plus c. All right, let's do a quick check. If I were to differentiate this, opposite cotangent of x is going to go to opposite of cosecant squared x. So that's cosecant squared x minus 1/4 times the derivative of an exponential function is the exponential function itself, times the derivative of the exponent, times the natural log of the base. And the derivative of any constant is, I'm going to include it. What the heck? Is 0. Did we get our original integrand? So big. I'm feeling good about that. All right, what questions do you guys have about number 3? A little bit of foreshadowing. Today we're going to develop our final antiderivatives, right? Our indefinite integral for our remaining trig functions. So that's pretty sweet. Lastly, let's go ahead and see what happens upon initial substitution, right? We always want to check and see if we can evaluate this limit through direct substitution. We put in no less than 2 examples last time, right? Don't be lulled into taking derivatives just because we're dealing with L'Hopital's rule of this section, right? We want to make sure we're always checking, because evaluating a limit, right, we must consider what the expression is tending towards at my x value of concern before we decide what technique we might want to apply or not. All right, as x goes to 0, what does the top do? Well, I'm getting 0 minus the sine of 0. That's approaching 0. All over, what does the bottom do? Well, x squared is going to 0 as well. Ding, 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 ding. We have an indeterminate form, indeterminate quotient that does authorize the use of L'Hopital. So because we have our indeterminate form that's 0 over 0, I'm authorized to, well, go to the hospital. I can rewrite this, right? I can rewrite this as the limit as x approaches 0 of the quotient of the derivatives, right? And so I'm going to take the derivative of the top, the derivative of the bottom separately, and try again. Applying L'Hopital's rule is easy if I already have a quotient. So here we go. The derivative of the top is 1 minus cosine of x. Yes, 1 minus cosine of x. Awesome. Love derivatives. They're so easy. So familiar. They're so comfortable. And try again. As x goes to 0, 1 goes to 1. Minus cosine of 0 is 1. So the top goes to 0 over 2 times 0 is 0. So big. I'm getting 0 over 0 gain. So, yet again, I'm authorized to use L'Hopital's rule. I'm going to show that with a little h there. I made that up. That's not a college board thing. That's just for me and you to see when we're applying L'Hopital's rule. And so it says, I'll consider the limit as x approaches 0 again, but this time, take the derivative of the top, take the derivative of the bottom, and then examine again. So here we go. Derivative of 1 is 0 minus cosine differentiates to opposite of sine. So negative cosine would differentiate to positive sine of x. Is that what you guys are getting? All over. There's a light at the end of the tunnel. I know I'm not going to be able to go anymore because my almighty bottom is 2. Right? The derivative of 2x is 2. Try again. As x goes to 0, sine of x goes to 0 over a constant 2 is overall 0. And so we finally made it to the end of the road. we don't have to write our limit expression anymore. And since I've got the space, just an opportunity to get a little bit more color. Splash involved. Oh yes. Raise your hand if you got all the way to the end. Who got 0 for your evaluation? That's great. So you're able to correctly apply L'Hopital's rule then, right? So long as we have an indeterminate quotient. Today we're going to take a step back and make sure we've got experience with an indeterminate difference, indeterminate product, and an indeterminate power. So that's what we're going to look at together today. Then I'm going to ask that you go back and complete your other indeterminate forms, the one that we only started together, that Tyler asked about last time. And if you have any problems with that, please direct them to Tyler. Keep in mind, Tyler is the one that brought it up. Tyler is the one that we suggested that we complete that for homework, and I was like, the nice guy, oh, no, hold off on that. We're going to do some more together, right? And then now you get to, Tyler. And so please direct any concerns about that to Tyler. Anyways, thank you, Tyler. All right, so let's go ahead and take care of our housekeeping first, though. At this time, I ask that you take out your OTL number 4. Please staple, right? Please staple your half sheet there. There's a graph on the back, so please staple your half sheet. Give yourself credit for those you completed out 22. I'm going to pause the recording now while we do our check. And Riley Freeman's in charge of... All right, so let's go ahead and remind ourselves about our indeterminate forms. Be ready, because I'm going to call on you. Go ahead and look at your closure from last time, if, right, you don't remember, because you know that I'm going to call on you. And you might think that I'm not going to call on you, but then, surprise, I would have called on you, so make sure everybody's ready, okay? So what are our indeterminate quotients, right? Our indeterminate quotients. Monica? Awesome. So our indeterminate quotient are infinity over infinity, and that's either of the, right? That's positive or negative, and 0 over 0. Great. What's our indeterminate product? So we have a single indeterminate product. What's that? Be ready? Joel?
0 times infinity.
Good. 0 times infinity is our indeterminate product. Here again, we've got a tug of war going on, right? Remember, we're not talking about 0 times some big number. That would equal 0. We're talking about a quantity approaching 0 times a quantity approaching infinity. So we've got a tug of war going on. If this first quantity is shrinking towards 0 more quickly than the second quantity is growing, it's going to pull the overall value of the product towards 0. On the other hand, if the second quantity is ballooning towards infinity more quickly than the other is shrinking, it's going to win the tug of war, and it's going to pull the overall value of the product towards infinity. And that's why this is an indeterminate form. We can't tell what the value of it is just by looking at it. In fact, that's where we have to consider rates of change of those quantities, and that's where L'Hopital's rule comes into play, right? Don't we take the derivative when we apply L'Hopital's rule? So we're getting those rates of change involved to see who wins, who grows, or who shrinks more quickly. That's what our derivative is telling us. Our indeterminate difference, we had a single form. What was that? Megan? Infinity minus infinity. Awesome. And the same thing is going on here. This isn't a number minus itself. Clearly that would be 0. There's nothing indeterminate about a number minus itself. But rather, we're talking about a quantity approaching infinity minus a quantity approaching infinity. If this quantity is much bigger, much more quickly than this one, it'll overwhelm the second one. And this subtraction, right, won't matter. It'll overall go towards infinity. However, if the second quantity is growing more quickly than the first and overwhelms it, it's pulling the overall value of the difference down towards negative infinity. So again, this is indeterminate. Or is there some break-even point, right? Do they settle into some sort of comparison in their rates of growth such that they're about equal, right? And then that ends up equaling 0 or some other constant. And lastly, indeterminate powers. These are the tricky ones that we're going to look at today. We had 3 different forms. Go ahead and tell the class one indeterminate power. What's one indeterminate power? Well, this is going to be fun. We got 3. Ha! Riley E. Bless you.
1 to the infinity.
1 to the infinity. Awesome. Everybody look. Again, it's not the number 1 multiplied by itself an infinite number of times. That would equal 1. There's nothing indeterminate about that. It's a quantity approaching 1, right? Multiplied by itself over and over again. If my quantity approaching 1 is approaching 1 from the left, that's numbers like 0.9, 0.99. When I multiply a number less than 1 by itself over and over again, it's pulling the overall value down towards 0, right? 0.9 times 0.9 is 0.81. Times 9 is 0.729. Thank you. And so on and so forth. So that's pulling the overall of the power, rather, towards 0. Conversely, if I'm letting x approach 1 from the right-hand side, number is slightly larger than 1, 1.1, right? 1.01. When I multiply that over and over again, it's ballooning towards infinity. It's getting larger, and so that's why this is indeterminate. All right, a different one. Riley F. I.
That'd be infinity to the 0.
Infinity to the 0. Nice job. 0 to the infinity would be no problem. If my base is approaching 0 and I'm multiplying the smaller number over and over again, that's going to pull towards 0. But infinity to the 0 is definitely indeterminate. My base, right? My base is trying to bring the overall value towards infinity. My exponent is trying to bring the overall value towards 1. And who's going to win? We don't know. We're going to have to get our rates of change involved again to determine the winner here. And lastly, finally, F R.
0 to 0.
0 to the 0 is indeterminate. My base is trying to bring the overall value of this power to 0. My exponent is trying to bring the overall value of my power towards 1. And so again, we've got a battle. We don't know who wins or not. All right. Great. So those are our 1, 2, 3, 4, 5, 6, 7 different indeterminate forms. Of those 7, only 2 authorize the use of L'Hopital's. Which are those, James?
Just the quotient.
Just the quotients, right? These are the only ones that authorize the use of L'Hopital's rule. Awesome. So what happens when we run into a situation where we don't have an indeterminate quotient? So everybody, please go back to your number 2 where we said left off. And Tyler was like, please, can't we do it? Please, please, Mr. Fritz. And I was like, oh, I'm going to have to hold off. So go back to yesterday's, please, 6-5, other indeterminate forms. Take a look at number 2. Initial substitution results in 1 over 0 is infinite. Minus 1 over e to the 0 is 1 minus 1 is 0. Minus 1 over 0 is infinite as well. So notice how we have an indeterminate form. There's our indeterminate difference. However, only our squiggle outline popcorn indeterminate form quotients authorize the use of L'Hopital's. So what technique are we going to be able to use to rewrite this into an indeterminate form that does authorize the use of L'Hopital's? Well, we've got fractions. Some are different fractions. And back from elementary school, how is it that we combine multiple fractions, right, through addition or subtraction? What do we first need? Kyle? Yeah, we need a common denominator here. So we're going to go ahead and create a common denominator. And so let's go ahead and write that technique here. We'll do common denominator. And let's go ahead and rewrite my limit. So the limit is x approaches 0 of so this first fraction needs an e to the x minus 1 over e to the x minus 1. The second fraction needs an x over x. Is that right? So we'll go ahead and combine my fractions now that I've created a common denominator. A sum or a difference of individual fractions, right, is equivalent to the sum or difference of the numerators all over that common denominator that we just created. So we'll go ahead and do another one. Another rewrite. On top we have e to the x minus 1 minus x. On bottom we have our common denominator that we constructed, and that was x times quantity e to the x minus 1. Let's pause and make sure we're all there. So we went ahead and we created a common denominator by multiplying the first fraction by a clever one, e to the x minus 1 over e to the x minus 1, so that it had the same denominator as my newly created denominator on the other one. I multiplied by x over x. And now we have a common denominator of x times e to the x minus 1. Everybody good? All right, so what do we do now? We try again. As I plug in x equals 0, I'm getting e to the 0 is 1, minus 1 is 0, minus 0 is 0. So my numerator is 0. What happens to my bottom? Well, I get 0 times 0 is also 0. So it looks like, voila, by utilizing a common denominator, nice technique, Kyle, I've constructed an indeterminate quotient form which does authorize the use of L'Hopital's. So now, check, I can go to the hospital. So I'll go ahead and show that with a little that, a little h there. We're going to apply L'Hopital's rule in this step. So now we'll consider the limit as x approaches 0 of the derivative of the top over the derivative of the bottom. So we'll differentiate the top term by term. We'll differentiate the bottom separately, and we'll try again. So the derivative of e to the x is e to the x minus the derivative of 1 is 0 minus the derivative of x is 1. So e to the x minus 1 is my top derivative. You guys get that? Bottom derivative. Oh, crikey. What rule do we have to use to differentiate that bottom? Right? What rule are we going to have to use to differentiate that bottom? Evie? Product, right? Absolutely. Thank you. So the derivative of product of two functions is the derivative of the first times the second plus the first times the derivative of the second. The derivative of e to the x minus 1 is just e to the x. So we differentiate the top, we differentiate the bottom separately, and now we'll try again. So as x goes to 0, my top e to the x is going towards 1 minus 1 is 0. Over my bottom is going to e to the 0 is 1 minus 1 is 0 plus 0 times 1 is 0. 0 plus 0 is 0. Oh no! Do we quit? No, we're just authorized to use L'Hopital's rule again. So let's go ahead and use L'Hopital's rule again, where we can consider the limit as x approaches 0, but now we'll differentiate the top yet again. The derivative of e to the x is e to the x over, on the bottom, I do not need to use the product rule for this first term. This first term, that is just a constant multiplier of 1, so I can disregard that. The derivative of quantity e to the x minus 1 is e to the x. However, in the second quantity, e times e to the x, I do have to use the product rule. So I'm going to go ahead and use the product rule for the squiggle underlined red. Product, x times e to the x. Here we go. The derivative of the product of two functions is the derivative of the first times the second plus the first times the derivative of the second. What's the derivative of e to the x?
E to the x.
E to the x, comma, baby. It's my favorite derivative. Oh, and integral. All right, let's try again. As x goes to 0, e to the x goes to
1.
Hey, I'm not going to be able to use L'Hopital's rule, right? For better or for worse, I'm at the end of the road here. I know that we won't be doing L'Hopital's rule anymore because my top is in 0 or infinity. Let's check out the bottom. As x goes to 0, e to the x goes to 1 plus 0. Is this indeterminate? No, I'm ready for direct substitution. My x value of concern is in the domain of the expression. I get 1 over 1 plus 1 is 1/2. I'm getting 1/2. That's pretty sweet. So did the first infinity grow more quickly? Did the second infinity grow more quickly? Who won this battle? It looks like they evened out and approached some constant, which is oftentimes the case when you have an indeterminate form. It ends up being something like 5/4 or -7/3 or 1/2. So that's pretty sweet. Awesome. So not only can we handle indeterminate quotients, we can also handle indeterminate differences. Let's go ahead and take a look at an indeterminate product. And so everybody, this is in today's note sheet now. The rest of that, right? Well, it's the same one, isn't it? Is this the same one? Okay. So we're going to do one more so that you don't have as much homework. Oh, nice guy teacher being plastic. Let's go ahead and consider number 3. Is this number 3? So as x approaches 0 from the right, let's consider what happens to the value of my original expression x ln x. And so as x is approaching 0 from the right, 0 is going towards 0. And natural log of x is going towards negative infinity. Is that what you guys are getting? So my natural log, right, goes towards negative infinity as x goes to 0 from the right. And so 0 times one of the infinities is an indeterminate product. If the first quantity shrinks to 0 more quickly, it'll pull the overall value of the product to 0. If the second quantity goes to negative infinity more quickly than the first one shrinks, it'll pull the overall value towards negative infinity. Keep in mind that depending upon which direction 0 is being approached from, positive or negative, it could change this to a positive infinity. And so we've got all kinds of possibilities here, and that's why it's indeterminate. So what are we going to do? Well, let's see if we can't rewrite this as one of my indeterminate forms that does authorize the use of L'Hopital. So which one is authorized the use of L'Hopital? Only the quotients, and right now I have a product. How can I rewrite this product as a quotient? Well, here's a little tricky way. We could go ahead and not take L'Hopital's rule, right? We only do that if we have a quotient. Instead, rewrite that x on top as its reciprocal. That is multiplying, right? Multiplying is the same as dividing by the reciprocal. What? Well, we're not used to saying it that way. We're used to saying dividing is the same as multiplying by the reciprocal. So then it makes sense that multiplying is the same as dividing by the reciprocal. I'm going to take that x on top and rewrite it as 1 over x. It's reciprocal on bottom. So I'm going to go ahead and rewrite that x as 1 over x on bottom. I'm going to leave the ln x on top. And so that was just a tricky way of rewriting multiplication as dividing by the reciprocal. Why in the world would we do that? Well, now at least we have a fraction. Let's see what the value of this fraction is. If it's an indeterminate form, we're good to go with L'Hopital's rule, all right? And this will have worked. So as x goes to 0 from the right-hand side, my blue ln of x goes towards negative infinity, right? Ln of 1 would be 0, but this is going towards negative infinity, so my top is negative infinity. Oh, jeepers. Over, and as x goes to 0, but from the right-hand side, 1 over x. Well, 1 over x is my hyperbola branches, right? My hyperbola branches, the swoops, right? The swoops. And so as x goes to 0 from the right-hand side, what are my hyperbola branches doing? What are my y-coordinates doing? Positive infinity. Ding, 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 ding. We've gotten one of our indeterminate quotient forms. Plus or minus infinity over infinity authorizes use of L'Hopital's. And so that rewrite as a fraction was the way to go, because now we can go to the hospital. Right? We're going to apply L'Hopital's rule. So we'll consider the limit as x approaches 0 from the right. But now we're going to go ahead and differentiate the top. Differentiate the bottom separately, and then try again. So here we go. What's the derivative of ln of x? Can I check? Yeah, 1 over x. Yes. Separately, we'll differentiate 1 over x. And that is power rule. Current exponent is -1. So -1 x to the -2, which is -1 over x squared. That's pretty sweet. Right? So if I simply evaluate it now, right, I would continue to get 1 over 0 is infinity over 1 over 0 is infinity. I continue to get infinity over infinity, right, here, forever and ever. Instead, let's rewrite this complex fraction. Take a look. I've got a fraction over a fraction. Let's go ahead and rewrite this top fraction, 1 over x. Right? Let's go ahead and rewrite that on bottom as x. Let's rewrite this bottom fraction, -1 over x squared. Let's rewrite that as x squared on top. And now consider the limit as x approaches 0 from the right. Well, isn't that the same as the limit as x approaches 0 from the right of negative x? Yes, doesn't that reduce? Is 0 in my domain of my expression?
Yeah.
Can I evaluate this limit through x substitution? Yeah. And so this now is just equal to 0. Back to my original product. Who won in the initial battle between x and ln x? Who won? Yeah, that first term, which happens to be a linear term, right? A linear term is a special power, right? It's just x to the first. That power, right, is going to grow more quickly than the natural log, right? Than the natural log. And so it looks like that first one won out, and this one pulled the overall value towards 0. That's pretty sweet. All right. So what do we want to do? This one is not on your note sheet. So this one is not on your note sheet. I want to take one look at the indeterminate power, and I don't want to steal your fun. So this one is today's notes. If everybody could please find day 5. I did include an indeterminate power because this will be similar to the technique we learned 2 class periods ago in order to rewrite as one of our indeterminate forms. So here we go. The limit as x approaches infinity, this will be the last one we do together today, as x goes to the 1 over x. So here we go. Initial substitution. I consider the value of the overall expression. It looks like my base is approaching infinity, raised to 1 over a quantity approaching infinity. My exponent is approaching 0. Is infinity to the 0 an indeterminate form? Certainly. If it had been 0 to the infinity, then that would be determinate and it would equal 0. But this is indeterminate because, again, that base in this power is trying to turn the value towards infinity. The exponent is trying to bring the value towards 1. We don't know who wins. We've got a tug of war. So we're not going to be able to tell what the value of this is just by looking. It's indeterminate. That's okay. We're going to go ahead and rewrite this as one of our forms that authorize the use of L'Hopital's. But to get there, we're going to have to do some finagling. That is to say, let's let our original equal, let's let our original equal y. Right now I've got a variable expression up in my exponent, and yet in this chapter, in this unit, right, we've been getting that variable expression down out of the exponent, and how have we been doing it? What's enabled us to get those variable expressions down out of the exponent? Right, what have we been doing? What's that? Yeah, natural log. If we take the log of both sides, that'll get our log properties involved, and we can now bring down that exponent as a multiplier in front. Excellent, thank you. Let's go ahead and take the natural log of both sides. So our first step will be to take the natural log of both sides. It's just that we're taking the natural log of both sides. I am taking the natural log of a limit, right? In order to utilize the natural log properties to bring that exponent down in front, this needs to be the log of a power. And right now it's a log of a limit. Don't worry, that last property underneath corollary 2 on your handout for L'Hopital's rule is the function interchange theorem. It allows us to take the function of a limit and change it as the limit of the composition of functions, so long as my function is continuous at the x value concerned. And here we're letting x approach infinity. Is my function continuous then? Well, yes, my function is continuous. I've got no problems there because we're not approaching, well, we could be approaching 0 from either side, it would still be okay. But we're going to use the function interchange theorem so that we can flip the position here of my limit and my logarithm. We're not going to do the log of the limit, we're going to do the limit of the log. So we'll go ahead and leave the left-hand side alone. Still natural log of y. We're going to apply the function interchange theorem for continuous functions, which allows us to consider the limit of the natural log of x to the 1 over x. And now we can utilize our logarithmic properties. Did you see that? That's pretty sweet. Because now we can bring that exponent down with the variable expression in front of the multiplier. So that's pretty cool. Let's go ahead and keep our L and Y. Let's keep our limit. Let's bring down our exponent. Let's rewrite that 1 over x times ln x as a quotient because we're aiming for, right, we're aiming for L'Hopital's rule here. And we know that only quotients authorize use L'Hopital's. So we'll keep the limit as x approaches infinity. But we'll rewrite 1 over x times ln of x is what? Well, how about ln of x over x? Now let's consider the value of my input as x approaches infinity. As x approaches infinity, natural log of x approaches what? Infinity, albeit slowly. As x approaches infinity, x approaches infinity. So guess what? Dun, 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 dun. We've generated an indeterminate form that does authorize the use of L'Hopital's. So we're ready to go. Notice how the left-hand side is still ln of y. However, the right-hand side now becomes the limit as x approaches 0 of the derivative of the top over derivative of the bottom. What's the derivative of ln of x? 1 over x. Wait for it. What's the derivative of x? Oh, I love that one. Gosh, I love the derivative of x. Let's try again. So this whole shmam ends up being easy to evaluate. We just need to consider what happens to the expression 1 over x as x goes to infinity. What happens to this quotient as x goes to infinity? What's that? It approaches 0, right? As x goes to infinity, 1 over x goes to 0. The denominator of this fraction balloons. So guess what? ln of y equals 0. But we weren't asked to evaluate ln of y. Our original limit, as x approaches infinity of x to the 1 over x, was y. And so if ln of y equals 0, what must my original limit, which we named y, what must my original limit y equal? Yeah, e to the 0. E to the 0. So my original expression that I named y equals 1, which means that after all that, the limit as x approaches infinity of x to the 1 over x is equal to 1. That's pretty sweet. Okay, I'll put one more time. I don't want you to think the calculus class is like boring or whatever. Awesome. At this stage, we've taken a look at lots of indeterminate quotients. We've taken a look at an indeterminate difference, an indeterminate product, and an indeterminate power. Your job then is going to be go back and complete 6.5 and check with the posted answer key on our Moodle site so that you can make sure you're comfortable handling those indeterminate forms that aren't quotients. All right, now we're going to switch gears. So today we're going to develop our final antiderivative. There are antiderivatives for our remaining trig functions. So we're going to complete a jigsaw. And I've done this differently each year. So what we're going to do this year is we're going to do this in our, I think it's going to be better having 4 minds thinking together than it is having 2 heads thinking together. So in the past I've done it as partners. In the past I've done it with me leading them, but we just did a whole day of L'Hopital's rule with me leading, and so it's time for us to get back in our groups and have some interaction. So what I'm going to do is we're going to break into our groups, and then I'm going to go ahead and distribute a single form, Form A, to all 4 of you. I'm going to distribute a Form B to all 4 of you, and then we'll jigsaw by sharing one group shares with another group. And so once again, I'll pause the recording, and we need our new groups. We share our findings, okay. May I have your attention, please? Thank you. Let's go ahead and see how our jigsaw went. And so we now have all of our antiderivatives for the transcendental trigonometric function. I'm going to go ahead and get rid of this. So we already have an antiderivative for sine of x. Be ready, right? Because I'm going to be calling on you. So what's an antiderivative for sine of x? What's an antiderivative for sine of x? Hayden?
Negative cosine x plus c.
Good. And so the derivative of negative cosine of x, right, would equal the positive sine of x. Therefore, an antiderivative of sine of x is negative cosine of x. Nice job with the signs, Hayden. What's an antiderivative for cosine of x? Be ready. What's an antiderivative for cosine of x? Michael?
Sine of x plus c.
Absolutely, and thank you for including the constant integration. You guys are doing great. So we already know an antiderivative, right, for some trig functions. Let's add our remaining ones. And so what's going on with the antiderivative of tangent of x? Well, in order to do that, we had to rewrite using the quotient rule. But the reason we did that and justified our steps is now, forever after, we can simply use our shortcut antiderivative rule, if you will, right? And so what's an antiderivative now for tangent of x? And you can go right to the answer. We've got 2 different ways to express it. And so who out of my group A's out there? You guys are group A's. So what's an antiderivative? Riley E?
Opposite ln
Nice job. Please note that the opposite of natural log of absolute value of cosine of x plus c is also equivalent to what you'll more frequently see on the AP multiple choice test. If we took this negative and put it up on top of my input in accordance with the log of a power property in reverse, so if we took this negative multiplier and put it on top as an exponent of negative 1, we could rewrite this as the natural log of cosine of x to the negative 1, which is equivalent to the natural log of 1 over cosine. What, though, is 1 over cosine? What's the identity for 1 over cosine? Secant. And so I want you to know that you'll see this in multiple choice tests written as natural log of secant of x as well. Either one is fine with me for you to use during classroom tests or quizzes. So once again, you would use either form, opposite of natural log of cosine of x plus c, or natural log of absolute value of secant x plus c. In each case, you must have absolute value bars, right? Both of those function inputs, cosine and secant x, produce negative values for some values in their input. Therefore, you have to include absolute value bars whenever you're taking an antiderivative involving natural log rule. Great. Go ahead and share Form B'ers out there. The antiderivative for cotangent of x. How am I going to write the antiderivative for cotangent of x? And so that was, Form B'ers are like, Sophia? Natural log of absolute value of sine of x, closed bars plus c. Awesome. And so now we have an antiderivative for cotangent of x, and forever after we can go straight to the shortcut rule. So you don't have to rewrite it as the quotient and apply the natural log rule each time. You can go right to your answer forever after. So again, you can add these to your flashcards. You can add these to your your nightly flossing routine, flashcard routine, and antiderivative for secant of x, right? Back to our form A here, so an antiderivative for secant of x. Colin?
ln absolute value secant x plus t.
Awesome. And those t's and pluses and x's all right next to each other, close proximity, danger. Danger. And lastly, our antiderivative for cosecant of x, and so an antiderivative for cosecant of x. And so we have form beers here. Riley, F, we have form beer?
Yeah, the opposite of natural log of absolute value of secant x plus the tangent x.
Awesome. Awesome. And some of these could be rewritten in alternative forms, so make sure you check your integral tables on page 302. Ladies and gentlemen, wow! So we do have a little bit of time, and I was so worried about our L'Hopital application, but that's why we were scrunched last time. So I think in the future, I won't try to do all the indeterminate forms in a single day, because that was kind of indeterminate overload last class, if you know what I mean. In any case, we've got all our antiderivative rules now. Make sure you check out the integral table on page 302. Let's go ahead and finish it up with our closure. So when trying to evaluate a limit analytically, what should we always do first? Please write down a response and be ready to share. What strategy can be used to move a variable expression out of an exponent? That's shown up several times now throughout this unit. And we need to commit our final antiderivative rules to memory. So we need to memorize the indefinite integral of tangent of x, the indefinite integral of secant x, and for now you're welcome to look at your notes, right? But we need to commit those to memory now in the upcoming days. When evaluating a limit algebraically, what should we always try to do first? Please share with the class when I call on you. Tess?
Direct substitution.
Absolutely. We want to try to evaluate the limit through direct substitution to see what we're working with. Is it determinate? Is it indeterminate? Right? What strategies might we use to evaluate it? We'll only be able to ascertain the answers to those questions if we first do direct substitution. Awesome. Thank you. What strategy can be used to move a variable expression out of an exponent? We've seen this as a recurring theme throughout the unit. What can we do to get our variable expression down out of the exponent? What can we do? Maggie?
Take the natural log of both sides.
Absolutely. We can take the natural log of both sides, and then we introduce our log problems. Good job. Thank you. What's the antiderivative for tangent of x? Emily?
Opposite ln absolute value cosine of x. C.
Awesome. Thank you. Please note that's equivalent to the natural log of absolute value of secant of x, closed bars plus c. Either one is correct and fine for you to put on test or quizzes. Also note that either one could appear on multiple choice. And then lastly, what's an antiderivative for secant of x? What's an antiderivative for secant of x? Monica?
The natural log of absolute value of secant x equals tangent x.
Awesome work today, ladies and gentlemen. I'm going to go ahead and stop the recording and save these and get it up on our YouTube channel.